Hello everyone and welcome back. So in this video I will be deriving the expression for the electric field created due to a point dipole at its axial and equatorial position, and in the next video I'll be deriving a general expression for the electric field at any point that is inclined at an angle theta to the dipole. So an axial position in a point P at an axial position basically refers to any point that lies on the axis of the dipole, whereas the equatorial position refers to a point that is present on this perpendicular bisector. So with that out of the way, let's begin with the proof. We'll begin with the axial position. So that is the point on its axis. Now for that, let us draw a small diagram of sorts. Let's have our dipole. That's a minus q, this is a plus q. This is the center O. We can let this be points E and P, and this is the point P at which we wish to find the electric field. So this point P can said to be at a distance of r, I guess, from the center of the dipole, and we can say the length of the dipole is about d. So, oh wait, this is not in P. Yeah, so the length of the dipole is about d. So with this brief diagram out of the way, let's actually begin with the expression. Now the electric field at P is nothing but the vector sum of the fields due to both the charge plus Q and the charge minus Q. So we can write that over here. So we can say E net P is equal to E plus Q plus E minus Q. Now since it is a long, all the 3 points lie in a single line, we can quite clearly see that the electric field due to P, and since it's positive, will be pointing away from P, and if I suppose say this is the x-axis, then I can see that it is pointing along I cap, and the electric field due to minus Q is pointing along minus I cap because it's created due to a negative charge. And so if I were to consider only the magnitude, then I could say E net P is equal to E plus Q minus E minus Q. We are considering only the minus, so I've taken that minus charge into account and I'm simply writing the magnitudes. So now let's write the expression for the actual electric field due to each of the charges. Now the magnitudes will not be the same because remember that they are not at the same distance from the charge, say that is, they are not the same distance from point P. Charge plus Q is at a distance of say R minus D, and charge minus Q is at a distance R plus D by 2, and it's R minus D by 2. So while the magnitude of the charge is same, the distance is not the same, so the magnitude of the electric field will also not be the same. So let's just write E plus Q over here. E plus Q is equal to 1 by 4 pi epsilon naught Q by R minus D by 2 the whole square, and E minus Q is equal to 1 by 4 pi epsilon naught Q by R plus D by 2 the whole square. And so the net field is simply the difference between these two values as we have shown above, as I have shown above. And so E net is simply equal to Q by 4 pi epsilon naught into 1 by R minus D by 2 the whole square minus 1 by R plus D by 2 the whole square. And if we further expand that, we get Q by 4 pi epsilon naught, you can add this to be R square plus RD plus D square by 4 minus R square minus D square by 4. But remember, this is R minus D by 2 the whole square, so it would actually be plus RD. So that's plus RD by R square minus D square by 4 the whole square. So we can cancel the R square and the D square by 4s over here, and what we will be left with is simply, I believe, Q by 4 pi epsilon naught, and this 2RD over here, so you can add this 2Q RD by R square minus D square by 4 the whole square. Now over here, we apply the same assumption that we used in the last video. We assume that d, that is the length of the dipole, is much smaller than r, where r is the distance to that point P. And we apply this assumption because we assume it to be an ideal dipole, and in that case, we take the limit as d tends to 0. So d is always going to be much smaller than r. And keeping that in mind, we can basically assume this d square by 4 to be 0. Or a more rigorous treatment would take r square out of the bracket, and then it would take d square by r square plus to be 0. But the end result is the same thing. And what we actually arrive at is 2q rd by 4 pi epsilon naught r raised to 4, because we have assumed the d square by 4 to be 0, and we have r raised to 4, and then we can cut an r, we can have an r cube over here, and we observe that qd over here is nothing but the magnitude of the dipole moment of the dipole. So this can further be written as 1 by 4 pi epsilon naught 2p by r cube, which is the expression that is generally used to find the electric field at the axial position. Of course, the exact expression is the one that I've written over here, but in most cases you will find that the length of the dipole can generally be considered to be negligible, so that we can apply the approximation over here. So a number of observations can be made over here. Clearly we see that the electric field is directly proportional to 1 by r cube, whereas in the case of the point charge, it is directly proportional to 1 by r square. So the magnitude of the electric field decreases much faster with distance when compared to that of the case of the point charge. Along with that, I haven't really mentioned anything about the direction right now. So while we were deriving this expression, we assumed that the magnitude of electric field to the plus q charge is greater than that created by the minus q charge, and that's because it's closer to point P. So naturally, because the direction of electric field due to plus q was along I cap, and since the electric field due to plus q is greater than the electric field due to minus q, we conclude that the direction is along I cap. So if I were to write this in a vector form, I could further write E net is equal to 1 by 4 pi epsilon naught 2p by r cube. Only distance being that here I mentioned p to be a vector. And since the direction of p, that is the dipole moment, is along I cap, it's the same thing. So I could also suppose, if I wanted to, I could erase this p, and I could simply write p, but then I could write I cap to mention the direction being along I plus x-axis. So I think that concludes our first expression, and we move on to the second case of the equatorial position, that is a point on the perpendicular bisector. So if I scroll down over here, this is expression number 2, and this is the equatorial position. Alright, so again we begin with a small diagram of sorts. So let's have our dipole over here, minus q, plus q, and this can be the center O. This can be points A and B. And since it is on the perpendicular bisector, we consider a point, suppose, say P over here. And this is where we wish to find the magnitude of the electric field. Now, clearly, we know that the electric field due to a point charge plus Q always points away from the charge Q, right? So if you were to trace the line that's passing away from the point charge plus Q, we would find that the electric field due to plus Q actually points along this direction. And in the other case, we wish to find in the case of the point charge, we know that the electric field always points into the charge, you could say. So if I were to suppose trace a line like this, we know that then the electric field due to minus Q would actually point inwards like this. So what we need to do over here is actually find the vector sum of these two electric fields. So I could sort of write this be E plus Q and E minus Q. And of course, it is at a distance, suppose you could say this distance over here is R. Right, so that out of the way, and of course the length of the dipole over here is also d. So with that out of the way, we'll try to find the vector sum of these two vector fields. Now you could of course simply use the cosine rule, I guess, or the vector sum formula if you've learned that, but I think there's a more elegant way in this case to do it. And the elegant way basically consists of resolving the two components along some horizontal component like this and the vertical component along this direction and this direction. Yep. So what we actually find is that the vertical components are equal in magnitude and opposite direction, so they cancel out, and the horizontal components are equal in magnitude but in the same direction, so they reinforce each other. So instead of just stating that in words, let's actually state it through maths. So let's begin with the derivation. Let's have E net. I can again say this to be equal to E plus Q plus E minus Q. But unfortunately in this case they do not lie in a straight line, and so we cannot simply write E net to be equal to E plus Q plus E minus Q, that is in terms of their magnitudes. But to write this in the form of vectors is perfectly legal, you could say. And so what I'll instead show is, let's first find the magnitude of E plus Q. Right? What is E plus Q? Now we can see that it is at a distance of, if I consider this to be about d by 2, this distance over here to be d by 2, and this distance to be r, then I can see that the length AP, which you really can't see point P written over there, so let me just make that clear. This is point P. The length AP over here is actually a root of r square plus d by 2 the whole square. So if I write that down over here, if I write the magnitude to be 1 by 4 pi epsilon naught q by r square plus d by 2 the whole square, and you will find that the magnitude of the electric field created due to the negative charge is also the same thing, because if you see, it's again d by 2 and it's again r square. So when you take the distance, suppose AP, you'll find that the distance is the same and the magnitude is therefore the same as well. So we find that it's 1 by 4 pi epsilon naught q by r square plus d by 2 the whole square. So, but they don't point in the same direction, so we can't simply just add or subtract. So what we have to do over here is actually resolve the electric fields along the horizontal and vertical direction and see what we get. And as we do that, I'll just redraw them over here down, just the electric fields. This is E plus Q, and this is E minus Q. So this is E plus Q, and I want to resolve it along the vertical direction and the horizontal direction. So let this be angle theta, and let this also be angle theta. So clearly the vertical component of E plus Q would be equal to E plus Q sine theta, and the vertical component of E minus Q would be E minus Q sine theta. But as you can see, since E minus Q is along the, you could say, third quadrant, that is, it is pointing in this direction, and E plus Q is pointing upwards over here, we find that E plus Q sine theta is along this direction, that arrow that I've just drawn, and E minus Q is along the other direction. And since E plus Q is equal to E minus Q, E plus Q sine theta will be equal to E minus Q sine theta, because angle theta is actually the same. So what happens is that the net vertical component, that is, if I were to write down over here, E net V is equal to E plus Q sine theta minus E minus Q sine theta. This whole thing is actually 0. So the end result is that we don't have a vertical component. We only have a horizontal component that sort of points over here. And what is this magnitude? Well, that is simply E net horizontal is equal to E plus Q cos theta plus E minus Q cos theta. and again E plus Q is equal to E minus Q in magnitude. So this is simply equal to, I guess you could say, 2E cos theta. Right, so till now, where E is where basically either E plus Q or E minus Q in the magnitude of E. But till now I have not actually said what the value of this angle theta is, or what this angle sine, what the magnitude of sine theta or cos theta could be. So to know what this magnitude could be, we go back to the figure, and let's and looking at this figure, you can see that at this angle over here, angle theta is equal to this angle over here, due to, well, I mean, this is basic geometry. So because they're alternate interior angles, I believe, so this angle theta and this angle theta are equal. Similarly, this angle theta, which is equal in magnitude to this angle, will be equal to this angle theta because they are corresponding angles. So you can clearly see that these two angle theta is actually the same, and we can then find sine theta and cos theta from this triangle over here, which is actually a right angle triangle, right? So keeping that in mind, let me just come up here and write the magnitude of sine theta and cos theta. Sine theta is clearly r by root of r square plus d by 2 the whole square, and cos theta is equal to d by 2 by root of r square plus d by 2 the whole square. So with this expression, we go back down and we write the magnitude of E net h, which is basically E net itself. Right, so this is going to be equal to 2q by 4 pi epsilon naught times r square plus d by 2 the whole square times d by 2 by root of r square plus d by 2 the whole square. So if we further simplify this, I can cut this 2 over here, and the expression, the value in the bottom, I can add that to, it's 3 by 2 power. So this will turn out to be 1 by 4 pi epsilon naught q d by r square plus d by 2 the whole square, or it's not whole square, it's actually 3 by 2 over here. It's r square plus d by 2 the whole square times the whole thing is raised to 3 by 2. And again, if I consider d to be much smaller than r, what I will end up with is this thing over here, which I can write to be E net. Finally, I can, of course, there's an approximation, but again, I mean, d is usually considered to be much smaller than r, that we can use the equal to sign Fe. So it's equal to 1 by 4 pi epsilon naught. And again, qd over here, up here, can be written as p. So this is equal to p by, we have considered d by 2 to be approximately 0. So what we are left with is basically r square raised to 3 by 2, which is nothing but r cube. And this is the expression that is commonly used for the electric field at the equatorial position. Again, a number of observations. We can clearly see that this expression is quite similar to the one that we derived for the axial position, except that it is half in magnitude to that, because for the above expression we had gotten 2p by r cube, whereas we only have p by r cube in this situation. Moreover, the direction over here is actually minus I cap. So if I were to write it along you could say in the vector form, I would actually have to write minus p 1 by 4 pi epsilon naught minus p by r cube, or minus I cap as I've written over here. And the reason for that is quite, and you can clearly see why it is so from the diagram, because although the dipole moment is along, say, you could say along this direction, in the electric field, when we do the resolving of the vectors, it turns out to be along minus I cap. So that is why we have chosen to, that is why the electric field is along minus I cap and along minus p vector. That is the dipole moment vector. So I think that's pretty much it for this video. Now in this video we only derived the expressions at certain positions, that is at angles, you could say angles theta is equal to 0 or pi, and at angle which corresponds to the axial position, and at angle is equal to theta is equal to pi by 2, which corresponds to the equatorial position. But what if the point P, suppose if I just draw a dipole over here quickly, what if the point P was at some angle theta? Well, in that case, we would have to use tools of multivariable calculus in order to find the net electric field at that point, because that is, we would have to take the partial derivative of the potential at this point, and that is why I actually chose to derive the potential in the previous video so that we could use it in the next video. So I think that will be pretty much it, and I'll see you in the next video. Thanks for watching.